Hi, this is Cao Song Huang of the Air Force Research Laboratory of the United States. My presentation is about long-lasting penetration electric fields and their effects on low-latitude ionosphere during geomagnetic storms. Penetration electric fields are the electric fields of solar wind magnetospheric origin observed equatorward of the inner magnetosphere, mostly observed in the mid and low latitude ionosphere. Penetration electric fields are caused by southward interplanetary magnetic field, the MF. So the penetration electric fields are highly correlated with MF reorientations. In this presentation, we will address the following outstanding problems. What determines the duration of short-lived 1 hour or shorter penetration electric fields? What is the maximum duration of penetration electric fields? Can shielding electric fields cancel penetration electric fields during southward MF? Can penetration electric fields dominate over disturbances dynamo electric fields during the recovery phase of magnetic storms? How significantly do penetration electric fields change the low latitude ionosphere during magnetic storms? In this slide, the left figure shows the first observations of penetration electric fields by Nishida in 1968. The MF turned southward with a quasi-period about 1 hour, and the northward magnetic field over the magnetic equator was enhanced during each interval of southward MF. The enhancement of the northward magnetic field is caused by an eastward Peterson current and eastward penetrating electric fields. The right figure illustrates the transmission of the solar wind or magnetospheric electric fields to the equatorial ionosphere. The solar wind electric field is first transmitted to the polar ionosphere along geomagnetic field lines and then to the equatorial region within the Earth's ionosphere waveguide or through compressional faster mode waves. This slide shows how magnetospheric electric fields can be shielded from penetration to the inner magnetosphere. Polarization electric field generated by charge separation in the ring current can shield the plasmasphere from the magnetospheric convection electric field. An equivalent scenario illustrated in the right figure is the radiant-2 field aligned currents can shield penetration electric fields. In general, it is believed penetration electric fields are shielded when the radiant-2 field aligned currents become comparable to or larger than the radiant-1 field aligned currents. Penetration electric fields occur during southward MF. After the MF turns northward, the electric field caused by the radiant-2 field aligned current becomes dominant, and it turned the shielding electric field. This slide shows examples of short-lived 1 hour or so penetration electric fields. The Chickamauga radar detected increases in the vertical ion drift in the desert equatorial ionosphere, which is the evidence of eastward penetration electric fields. Previous explanation was the duration of such short-lived penetration electric fields was determined by the shielding effect of a radiant-2 field aligned currents. The shielding time was proposed to be about 30 minutes. The implication is penetration electric fields could exist for only about 30 minutes, and then the shielding electric field would become dominant after this time scale. However, if we compare the equatorial vertical arm drift with the MF, we can see a very clear correlation between penetrating electric fields and MF southward turning. Each southward turning of the MF causes an increase in the vertical arm drift or eastward electric field. Each northward turning of the MF causes a decrease in the vertical arm drift, corresponding to a westward electric field. The new explanation is the duration of short-lived penetrating electric fields is caused by MF northward turning because the source of penetrating electric fields is terminated, but not caused by the shielding effect. The implication is penetrating electric fields can continuously exist if the MF remains southward. We searched geomorphic radar data over the last 20 years for penetrating electric fields. The criteria in our search is the correlation between the interplanetary electric field UY component, the IEF UY, and the atmospheric electric field UY component, the east-west component, must be greater than 0.8. In total, about 700 events of penetration electric fields are identified. The penetration efficiency is defined to be the ratio of the change of the atmospheric electric field to the change of the IEF UY. The numbers in the left figure represent the case numbers within 1 hour range in local time. The penetration efficiency is the largest around the local noon and becomes smaller toward afternoon. The penetration efficiency does not show a clear dependence on season. In this slide, the left figure shows the penetration efficiency as a function of the initial value of the IEF UY when the MF starts to turn southward. The penetration efficiency becomes higher when the initial IEF UY approaches zero. That is, when the MF changes from nearly zero to southward. The right figure shows the penetration efficiency as a function of the change of the IEF UY. The penetration efficiency is high when the change of IEF UY is small. A relatively small change in the IEF UY is in general corresponding to a rapid change in MFBG. Therefore, the penetration efficiency is higher for faster MF change. The straight line in the figure just shows a best fit line. This slide shows the relationship between the change of the IEF UY and the initial IEF UY. For initial IEF UY smaller than zero, the change of IEF UY is approximately 2 times the initial IEF UY. The result implies the MF or IEF variations are similar to a cosine wave. The change in the cosine wave from minimum to maximum is 2 times the initial minimum value, as plotted in the lower right figure. In the solar wind, the orphan waves have a typical period of 30 to 60 minutes. The eastward penetration electric fields observed in the equatorial atmosphere, as shown in the previous slides, often have multiple cycles. We suggest The short-lived penetration electric fields are often caused by orphan wave fluctuations in the EMF. We now present examples of long-lasting penetration electric fields longer than 2 hours measured by the Gigamarker radar. In the left figure, the EMF turned southward for 2 hours in a shaded interval, and the vertical arm drifts in the day-side equatorial ionosphere are increased by more than 100 meters per second over this interval. The change of the arm drift is well correlated with the change of the IMF or IEF. In the right figure, the green curve in the bottom panel represents the quiet time arm drift over Gigamarker, and the red dots represent the vertical arm drift during the storm main phase. The vertical arm drifts are increased continuously for 4 hours. In these examples, the radar measurements show penetration electric fields exist for 2 or 4 hours in the equatorial ionosphere. This slide shows examples of long-lasting penetration electric fields measured by the DMSP satellites over the magnetic equator near dusk. The MFBG is plotted in the top panel. In the second panel, the black curve represents the quiet time reference of the equatorial vertical arm drift, and the red dot represents the vertical arm drift during the magnetic storm. The vertical arm drift are enhanced in an upward direction, and the enhancement of the vertical arm drift is caused by eastward penetrating electric fields. The yellow shading denotes the intervals of continuous existence of penetrating electric fields. In these examples, eastward penetration electric fields exist for 5 to 7 hours during the main phase of magnetic storms, when the MF remains continuously southward. This slide shows the solar wind and geomagnetic activity during a magnetic storm. This is a very interesting case. The MF is continuously southward for about 24 hours. The yellow shading denotes the first 3 hours of the southward MF. This is the main phase of the magnetic storm. The gray shading denotes the first day of the storm recovery phase. The vertical dashed lines indicate the first half day of the recovery phase of the storm. The bottom panel shows the AE index. AE remains very large during the storm recovery phase, indicating magnetospheric energy is continuously injected into the ionosphere. This slide shows the equatorial vertical arm drift measured by 4 DMSP satellites at an altitude of 840 kilometers in the dusk evening sector. In the left panel, the green curve represents the quiet time reference of the vertical arm drift, and the red dots represent the measured arm drift. The right panels show the difference between the slow time arm drift and the quiet time reference. This difference is the net change of the equatorial vertical arm drift caused by the magnetic storms. The vertical arm drifts are increased in upward direction for 14 hours. Penetration electric fields are the dominant electric fields in the equatorial ionosphere for 14 hours. Disturbances in dynamo electric fields become dominant of 14 hours after the storm onset. This slide shows the ion density measured by 4D MSP satellite at 840 km altitude in the topside F region. The increase of the topside ion density is caused by upward movement of F region, corresponding to an enhanced upward ion drift or eastward electric field. The topside ion density is increased for 14 hours and then decreased. The increase and the decrease of the ion density are very consistent with the upward and downward ion drifts. The observations provide strong evidence of a continuous existence of eastward penetrating electric field for 14 hours, including 3 hours of the storm main phase and the first 11 hours of the storm recovery phase. This is the first observation of penetration electric fields for as long as 14 hours. The previous slides show the penetrating electric fields measured at a fixed location or a fixed local time. We now use the data measured by the COSPAR satellite to derive the local time distribution of penetrating electric fields. COSPAR satellite returned to the same local time at nearly the same longitude after 24 hours. In the examples, the green dots represent the ion drift data 24 hours before the storm onset, and the red dot represented ion drift during the storm main phase. The meridional or the vertical ion drifts are increased on the day side and in the post-sunset sector, and decrease in the post-midnight sector. In this slide, the left figure shows the net change of the meridional or vertical ion drift derived from the state of the satellite during multiple magnetic storms. This net change represents the net effect of penetrating electric fields on the equatorial vertical ion drift. The right panel shows the simulation results of local time distribution of penetrating electric fields. The observations are very consistent with our simulations. The local time distribution of penetrating electric fields is very important. We do not have simultaneous measurement of penetrating electric fields at all local times. With this local time distribution, we can use the measurement at one or multiple local times to derive the penetrating electric fields at other local times. This slide shows the effects of penetrating electric fields on the generation of deep plasma bubbles and wide plasma depletion in the equatorial ionosphere. In the plot of the ion density measured by the DMSB F14 and F15 satellites, the black curve represented ion density distribution with magnetic latitude during northward MF, and the red and the green curve represented ion density distribution during southward MF. The large density decreases occur at low latitude, and the little density decreases are caused by penetrating electric fields during southward MF. This slide presents the details of the topside ion density measured by the DMSB satellites. The left figure shows a very deep plasma bubble over the magnetic equator. The ion density is decreased by 2 orders of magnitude, and the vertical ion drifts inside the plasma bubble reach 2,000 meters per second. The very large ion drifts are caused by polarization electric fields inside the bubble. The right figure shows the ion density is reduced by 2 or 3 orders of magnitude over a latitudinal range of about 40 degrees. This phenomenon is termed wide plasma definitions. These measurements show how significantly the slow time penetration electric fields change the distribution of the equatorial ionospheric plasma. This slide shows how the generation of equatorial plasma bubbles or wide plasma definitions depends on the MF southward turning. In the left figure, the vertical axis represents the time delay between the MF southward turning and the occurrence of plasma definitions, and the horizontal axis represents the minimum value of the MFBG. In the right figure, the horizontal axis represents the maximum IEF-UY. The time delay becomes shorter when the magnitude of the southward MFBG or the positive IEF-UY is larger, indicating larger perturbation electric fields cause faster generation of plasma bubbles and wide plasma definitions. This slide shows the change of the ionospheric topside TEC measured by a low Earth orbit satellite during a magnetic storm. The blue curve represents the TEC before the storm onset, and the red and blue dots represent the TEC during the main phase of the magnetic storm. The TEC over the magnetic equator is reduced, but the TEC at the equatorial anomaly latitudes is increased by about 900%. This dramatic change of the TEC at a low latitude is caused by the equatorial superfounding effect that is driven by very large eastward penetration electric fields. To summarize, penetration electric fields can be the dominant electric fields in the equatorial ionosphere for 2, 6, or 14 hours, even during the storm recovery phase, as long as the MF remains southward. The shielding electric fields produced by the region 2 field aligned currents may exist, but cannot cancel penetration electric fields. The duration of short-lived or long-lasting penetration electric fields is determined by northward turning of the MF or by the arrival of the disturbances winds, rather than by the shielding effect. Slow-time penetration electric fields cause deep equatorial plasma bubbles, wide plasma definitions at low latitudes, and the TEC enhancement by 900 at the equatorial anomaly latitudes. So that's all I present. Thank you for your attention.